This is section 12.2 continued, part 2. This is what we did not finish in class. It's beginning on page 868, and this is with number 9. Now, just to take a peek at what we were working on, we were working on surrounding this area here with a dog run, and you'll notice we have a length here in yellow, we have a length here in yellow, and we also have this width. So we have 3 sides, and I believe we had 16 yards of fencing. So right here, 16 yards of fencing. We came up with 2 equations. One of them was for L of W. This was the length in terms of the width. Okay, the length in terms of the width. And then for the second, we came up with our area model. So this is going to be the area in terms of W. Now, we did not use X down below here. Take a look. Okay, if you recall, we have A of W is equal to 16W minus W squared all over 2. And we did this pretty systematically. You just have to check out the part 1 video, and this is all explained here. To follow through, this is where we're going to pick up right now. I've got 2 functions up top. The first one is A of W, and we can call this one, move this over, let's call this one L of W. All right. It says let's compare and contrast the graphs of these 2 functions. All right, L and A. L of W is the length of the dog run as a function of the width. A of W is the area of the dog run as a function of W. So both of them you put in the width, and for the first you get the length, and the second you get the area. Well, let's describe the type of function represented by each one. So what kind of function is L? Well, we know that L, oh look at L. I'm going to give you a hint up here. It has a degree of 1. So in that case, this one is linear function. Let's go ahead and highlight that. It's a linear function, and it is a straight line. All right, moving down here, it says the graph of A of W. This is an area model. So we know area is length times width, and how many dimensions? 2. Well, look up here. Look at the degree. This is, well, the graph is a parabola, but what's under here? This is a quadratic function. Part B, state the domain in terms of each function and the problem situation. All right, this is going to be critical and very difficult to teach through a video, but I want you to do your best here. Now, I'm going to model this through the graphing calculator. So let's take a look at our graphing calculator. All right, what I just did is I turned on my calculator, and these are the 3 functions for the area. And it might look a little bit confusing right here, but all 3 are the same. It's just a different way of entering in this same area quadratic. Up here, this first one, the blue one, that's primarily how you're going to enter it in if you're using one of the TI-83 older calculators. This one, we're using math print, so we can set up a fraction. And this one is in standard form, so we just divided this 2 into both of these. All right, let's make this a little bit larger so you can see. I'm going to take and I'm going to delete 2 of these. All right, I'm going to delete both of these. And I'm going to actually write the other function in L of W. So the L of W was, open parentheses, 16 minus X, and that was all divided by 2. All right, and why don't we just, let's double check that for a moment. We'll head up here. Notice, there it is, 16 minus X over 2. All right, here's the calculator again. Now I'm going to graph both of them. All right, here's my area model, right? 2-dimensional, so it's a quadratic. Here's my linear model. That's L of W. Okay, so we've got both of these. Well, my goal here is for you to understand what domain is. And we're trying to find the domain now of L of W. Now, L of W on my calculator, so which one is L of W? Is it the straight line or the parabola? Well, in our case, it's going to be the straight line. Here's the larger screen. Now, I'm going to hit the trace button. And you'll notice that my icon is blinking on the parabola. I want it on the red line, so I'm going to hit the up or the down key. There it is. Now I can trace along the line. Now I want you to ask yourself, could I keep on hitting this left key forever and ever? And the answer is definitely yes. I can go left forever. And I can go actually right forever. When we're talking about domain, right here, this domain. Domain is how far left and how far right can you go on that function. Well, I got to tell you, you can go forever. So what we say here is that it's going to be here a set of all real numbers. You can go right forever and you can go left forever. Now, technically though, in this problem situation, we're kind of stuck because in terms of this problem situation, the domain is, well, in real life, you're not going to go into the negative region. So let's take out the calculator and let me show you what I mean. All right. How about in here? We're on the red line for now. I probably am not going to be able to go down here. Okay, that would actually give me a negative length. And over here would give me a negative width. So I have to actually keep it in between two values. Now, in the first video, we figured out what those were. This is 0, and this is 16. So my domain has to be between 0 and 16. Can't go below and can't go to the left over here. And there it is. So this indicates that the width has to be less than 16 and greater than 0. Now keep in mind, if you did this, if you put an equal sign here and an equal to sign there, well, that's actually wrong because the width cannot equal 16 and it cannot equal 0, or you don't even have an enclosure in this real life situation. So I want to take out my eraser and get rid of those. All right, let's take a look at A of W. A of W looks like this. Here we go. A of W is the blue. So let's hit the trace button. We're going to go up to the blue. Let's see, trace. There we go. I need to come up. There I am. Now you'll notice, if we're just talking about the function, and this was not a real life scenario, then you could go left forever. Notice, it's going to continue to go to the left. You can't see it, but it's going to continue. And we could continue to go to the right. So the real domain of the function is the set of real numbers. Okay, so any number you want. Now, in this situation, once again, you have to stay in between this 0 and 16. You have to. It just doesn't make sense to go outside those limitations. So once again, I want you to remember that when you're thinking about domain, we think how far right and how far left can we go? And then make sure that on a test or quiz, you understand what it means to explain the domain in terms of the problem situation, like what in reality can happen. Moving along. All right, this next one here, it says determine the y-intercepts of each graph and interpret the meaning of each in terms of the problem situation. Well, all right, we've got to investigate y-intercepts. Here are the two graphs. Now, let me get another highlighter out. this green little highlighted region, that's going to be where the y-intercept is, and this little blue region is where another y-intercept is. So I would say that this point here, if you were to graph it and find out what that is, well, you know what? Let's do that for a moment. Take a look. This is pretty easy. All right, I'm going to ask you a question. If you're going to find the y-intercept, what do you plug in for x? Well, you plug in 0. So watch this. Second trace. We want to find a value, number 1, and I want to set x equal to 0. So there's the 0. Let's hit enter. And it gives me 0, 0. So that's one of the y-intercepts, 0, 0. And the other one, if I hit the up key, is 0, 8. All right, so let me write these down. This is 0, 8, and this one happens to be 0, 0. All right, well, all of our points are in this form. Width, comma, area, or W, comma, A of W. That's what our points are. Now, does it really make any kind of sense to have a width of 0 and either an 8 or a 0 for our area? It really doesn't even make any sense. So this whole problem, these y-intercepts in this problem are not relevant at all. They're not appropriate for this kind of situation. All right? They're not appropriate at all. And if you want to see what the book has for you, or let's take a quick peek at that. It says the y-intercept of the graph of the linear function is 8. It indicates the length when the width is 0, and it's just not appropriate for a dog run. It doesn't even make any sense. Same thing for the area. Let's move down. Part D. Describe the rates of change for each graph. Oh boy, this is a little difficult. I need to pull this picture down. So I'm going to just go ahead and clone this. All right. There we go. We've got a copy of it. Let's bring it down. From Integrated Math 1, we dealt with a lot of rates of change. And rate of change, we have something that represents that called slope. It's a slope. Well, for this linear function, well, that's not too bad. For this linear function, you'll notice we have some rise and run. I can rise, and that's a distance of 8, and then we can run all the way over to, well, that was 16. Now keep in mind, we went down 8, but then right 16. So my rate of change, my ROC, rate of change, meaning the slope, for that blue linear function right there, how about we say the slope of, we'll call that L of W, is equal to -1/2. But look at this one. Look at this problem. Is there really one slope I can find? Well, let me get a line here and check this out. Well, the slope could be that, or over here it could be this, or it could be right here. And what I'm trying to get at is that when we're dealing with a quadratic, it might have instantaneous slope. That's kind of a calculus kind of term right there. But the slope, the rate of change, is always changing. Okay? So let's take a look here. It states here that the linear function has a constant negative rate of change, and it's going to be -1/2. And then the quadratic has a varying rate of change. Hopefully you can see that. Number 10, determine the dimensions that provide the greatest area. Use the graphical representations to explain your reasoning. All right, I've got to grab this graph again. Let's pull this over here onto the screen. All right, I'm seeking a few things here. In order to maximize this area, think about this. This is made up of a bunch of points on this problem. Here are a bunch of points. And each point is in the form w, comma, a of w. So the width, comma, the area. Now, I would gather that you understand when we are going to move to the right a certain amount and then up, that this point is going to be your maximum. And that point we need to find. We have a calculator to do so. So check it out. Here's the calculator. Let's open it up nice and large for you to see this whole thing. Okay, there it is. I'm going to go second trace, and that's, I'm going to find the maximum, number 4. All right, so I need a left bound. I'm going to get a little closer to the point that I am seeking. There we go. Enter. Let's move over. Enter, enter. All right, I have a maximum of 8, comma, and then 32. 8, comma, 32. All right, so this point right here is 8, comma, 32. So it pretty much takes a, so how about this? It takes a width of 8, and I believe we're working in feet. Actually, is this one in feet? All right, I believe we're going to be working in yards. Okay, so we're going to head back here. We're working in yards. So 8 yards to maximize the dog run area of 32. Now be careful here. I just can't put feet right here. We're talking about area, so it's square feet. All right, very good. Hopefully that makes sense to you guys. 32 square feet is the largest size that these dogs are going to run around in when we add on this dog run area. Okay. Page 870, problem number 2. We're going to be working with first and second differences. This is a little different here, so bear with me. Table A and Table B. States tables A and B represent 2 different functions. One is a linear function and one is a quadratic function. All right? So we've got a linear function and one of them is a quadratic function. It says, which table do you think represents each type of function? Well, I do know that if I'm dealing with a linear function, I know that I'm dealing with a line, right? And I know it has a constant rate of change. So it's like walking downstairs. Rise, overrun, rise, overrun, rise, overrun, rise, overrun. So it's a constant rate of change. So I do notice that, look what's happening. If I start at 6.5 and go to 0.75, well, I just added on 0.25, plus 0.25, plus 0.25, plus 0.25. Okay? I'm adding on the same thing. I just added on plus 0.25. That's a constant rate, so table A has to be the linear one. Okay? Let's point that. Linear function's right there. Now, this next table, you'll notice that it does not look like I have any kind of constant rate of change, does it? No. If I take out my calculator, we can kind of do some exploring here. How about I do this? Let's clear this out. I get to a nice blank screen. And let's try, how about 13 minus 6.75. All right, I got 6.25 there, so the difference between these was 6.25. And how about the difference of these? If I do 6.75, okay, minus 0, well, that's going to be 6.75. All right, and how about about these two. If I do 0 minus negative 7.25. Let's see what happens there. So 0 minus negative 7.25. That looks like it's going to be 7.25. That's pretty easy, right? And finally, right here, let's do negative 7.25 minus a negative 15. So I'm trying to find the distance between them pretty much, and that's going to be 7.75. Doesn't look like these are the same, does it? All right, so early indications lead me to believe that that this table B is going to be my quadratic. Took a lot to get there, right? You probably could have just looked at it. Here is kind of a solution they give you. I think that table A represents the linear function, and then we have table B is the quadratic function. All right. Okay, as you're reading down your page, if you want to pause the video, that's fine. I want you to be able to read this. I put this little reminder in there, even for me. So recall that first differences are the differences between successive output values when successive input values have a difference of 1. Now, there's a lot going into that statement. I want to show you what this means. So I've got this next page here. Let's take a look at this next page. I hope you all agree, if you're watching this, that these are the tables right from the last page. And I'm going to find the first differences, and I did that pretty much before. But let's do this officially out. I'm going to subtract this 7.5 and 7.25, and we get 0.25. Let's subtract these two. So 7 and 7. So 7.25 minus 7. That's going to be, again, 0.25. Next one. 0.25. Next one. This should be, I think I typed this incorrectly. It should be 6.5 right here. Okay. Let's make sure that that's really easy to read. So let's just go ahead and change it to 6.5, and that should be 0.25. Notice, look, they are all the same right here. Completely all the same. Those are the first differences. Now, that statement from the last page, let's read that again. Look at this statement. In order to find these first differences, they have to be from successive output values when the successive input values have a difference of 1. What do they mean? Look at this. Do we agree that all of these are 1 apart? Yeah. So you can even count them out. So negative 2 and then negative 1, 0, 1, and 2. They are 1 apart. The only way you can figure out first differences is if your input values, your x values here, are 1 apart. All right? Let's find the first differences for table B. And we pretty much just did this, but let's do it again. I'll start from the bottom. Let's do this 13 and 6.75. Well, that's going to be, we had it on this last page here, you'll notice. You can kind of see we have 6.25, 6.75, 7.25, and 7.75. All right, and it's kind of, there's a pattern there, isn't it? So we pretty much, we went up by 0.5, and then went up by 0.5, up by 0.5. Let's do that again on this page so we can organize it. All right. So right here, let's do 13 minus 6.75, and that's going to be 6.25. Next one, 6.75 minus 0 is 6.75. Next one, 0 minus negative 7.25 is going to be 7.25. Next one in blue, negative 7.25 minus a negative 15 is going to be 7.75. And you can take out your calculator and figure that out. That's fine. All right, notice all of the first differences for the linear function and notice that these first differences are actually different. So table B was our quadratic. Table A was our linear function. And we have these first differences that are, and we kind of call these constant because they are all the same number. So for a linear, first differences are constant. And for a quadratic, these first differences are actually different. Now I'm going to take this a step further, and this is probably this is going to be explained later on in the lesson, but watch this. Let's take this word different, move it out of the way for a moment. And now what I would like to do is let's find these differences. All right, follow me here for a moment. Let's do 7.75 minus 7.25. I hope you all agree that that's going to be 0.5. Let's do the next one. The next one is going to be 7.25 minus 6.75. That's equal to 0.5. Next one. 6.75 minus 6.25. And that is again equal to 0.5. Well, if these are your first differences right here, okay, these are your first differences, well, I can only imagine what we can call these, right? These are going to be our second differences. All right. What are we going to take away from this? That if you have a quadratic, the first differences are going to be different. The second differences are going to be constant. They're all the same number. Kind of one way to tell whether a function from a table is linear or quadratic. All right. Page 871. It says here, the graphs of two functions are shown. The two equations that represent the linear and quadratic graphs are, so we're given two equations here. Okay, so kind of take a look at them there. I noticed that the degree of the first one is 1, and the degree of the second one is 2. I call that a degree. That's a little bit more than what our book does, but that's called a degree. Number 3 says, identify the graph that represents table A. Well, table A was our linear function. And then the graph that represents table B. Table B was our quadratic. All right, so here we go. There's your linear function. And here is your quadratic. So you've got a parabola and then you've got a line. Number 4, describe the rate of change for each. Well, the rate of change, let me do some highlighting here. Let's highlight this one yellow. That's the linear. Okay, so the rate of change for that one. The rate of change, is going to be constant. All right, and the rate of change happens to be here. We could go ahead and figure all of this out, but it's going to be negative 1/4. And I'm going to use m because we know that rate of change is the same thing as slope. Now you might be thinking, how in the world did he get negative 1/4? Well, if you recall, look at this over here. Isn't this in y equals mx plus b form? Mx plus b, m being negative 1/4. There's your slope, your rate of change. This thing drops down 1/4, 1/4, 1/4. Now, the rate of change for this one, this quadratic, well, that rate of change varies throughout the entire, there's no one rate of change. Okay, so that is going to vary. The book indicates the linear function has a constant negative rate of change. Remember, negative 1/4. The quadratic function has a changing rate of change. Very good. Number 5, determine the y-intercept of each function. All right, the y-intercept. We head back up here. Y-intercept. We need to be looking in this region, folks. Let's focus right there. Okay? So I'm going to be looking at, let's get a red marker out here. I'm going to be looking at that point and that point. Those are two y-intercepts. It looks like for the parabola, this point here is 0, 0. That is a y-intercept. And this particular point right here is the y-intercept for that linear function. Now, I don't know what that is. It looks like it's a little bit more than, let's see, this is going by 5, so 5, it's somewhere in between here. Oh, but look up here. Y equals mx plus b. Do you remember what your b is? There's your y-intercept. It's 0, 7. Now that we found both y-intercepts, I just want to make sure, I've got this blinking highlighted yellow thing. I want to make sure that you understand that all y-intercepts are in the form of 0, a number. Okay, and when you want to find any kind of y-intercept, you plug in or you let x equal 0. All right? Okay. Page 872. Now we're going to be talking about this thing that is very important. It's called the leading coefficient, the LC. Leading coefficient of a function is the numerical coefficient of the term with the greatest power. So recall that a power has two elements. A power is a base and an exponent. So it says here in number 6, identify the leading coefficient of each function, then describe how the sign of the leading coefficient affects the behavior of each graph. All right, so we're going to be locating the leading coefficient, folks. Let's make this a little bit smaller. All right. Let's talk about this first one. This leading coefficient. So the LC, leading coefficient, is equal to negative 1/4. All right, negative 1/4. And what does this really tell us? This tells us, for this linear function, it's the slope. Okay? And it also tells us that since it's negative, it's going to be going down to the right. This next one here, we'll take a look. Here is your largest exponent. This is the term right here with the largest exponent. So the leading coefficient, again, would be LC, is going to equal negative 1/4. Now, when we get to integrated math 3, you're going to think of this negative 1/4 as kind of a stretch factor. It's kind of like a vertical stretch factor. Now, let's maybe not pay attention to the vertical stretch factor for a moment. Let's think about what this does for us for a moment. That negative indicates that this parabola is going to open downward. That's all we need to be concerned with right now. This is going to open downward. That's what the leading coefficient is going to do for us. Page 872. So it says, let's explore the table of values one step further and analyze second differences. Now, I did that with you a little bit, so you should be okay. I probably can go through this a little bit quickly. It says, calculate the second differences for each function, and what do you notice? All right. So once again, here are our second differences. We didn't find second differences for the linear function, though, and I can do that right now. If you have no idea kind of what I'm talking about, let's talk about right up here. I found first differences, but let's find the second differences. All right. Let's move this out of the way. Move this out of the way. What is 0.25 minus 0.25? Well, that's just 0. Once again, 0.25 minus 0.25, that happens to be 0. And finally, 0.25 minus 0.25 is equal to 0. So, what are you going to take away from this? Well, first differences are constant for a linear function, but then second differences are 0. Look down here. For a quadratic, the first differences are different. Second differences are constant. What do you think the third differences would be? 0.5 minus 0.5 would be 0. Hopefully you kind of understand and you see that pattern happening. All right, let's take a look at this problem number 3. It says, analyze the form of each equation and determine if it's linear or quadratic. Well, I mean, this is pretty simple. If we take a look at y equals 2x, what's the degree of this function? It's a 1. So this is obviously going to be linear. So let's check to see if these input values are consecutive. So if I start at 0, let's say, goes to -1, then goes to -2, then -3. Those are consecutive. Then in the opposite direction, 1, then 2, then 3. Those are consecutive. So it looks like we're on the way to finding first differences and second differences correctly. When we plug in here, right inside this first box right here, what do you think lies in here? Well, let's take this -3 and plug it in. Okay, if we plug that in, we're going to get, that's going to be -6. Okay, when we plug the next one in, 2 times -2 is negative, and that's going to be -4. Okay, and we can kind of finish this out. This is going to be -2. And then this 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. And 3 times 2 is 6. Okay, it's time to find first differences. All right. Tell me what's underneath here. If we want to find these differences, well, we could do -6 minus -4. So off to the side, watch. -6 minus -4. And that becomes -6 plus 4. And that looks like it's going to be a -2. But you'll notice these aren't really written in here correctly. They're cut out a bit. But they, instead of doing -6 minus a -4, they did -4 minus a -6. If that's confusing to you, here, let me just rewrite it. There's nothing wrong with what we did, but let's do -4 minus -6. Hopefully you see that that's a 2. Then negative 4, well, sorry, negative 2 minus negative 4, well, that's another 2. And we're going to get 2's throughout here. So let's fill these in. This is a 2, 2, 2, and this is a 2. And now the second differences. Well, 2 minus 2, 0, 0, 0, 0, and 0. Okay, so for the linear function, second differences are 0. Let's move on to b here, 2x squared. All right. Let's figure out what this one is. And these are successive, aren't they? They're consecutive. So we're okay. We're given the green light, we can find these first and second differences. Let's plug in negative 3. What's negative 3 times 2? Well, negative 3 times 2 is, well, actually, we've got to square it first. Let's just make sure that we do that correctly. Okay. So let's do a little bit of work right up here. This is going to be 2 multiplied by negative 3. And then that's going to be all squared. So that's going to be 2 multiplied by, well, negative 3 times negative 3 is 9. That looks like it's going to be 18. All right. So this is going to be 18. Okay. Let's plug in again right here. So negative 2 squared is 4. 4 times 2 is 8. And plugging in negative 1 squared is 1 times 2 is 2. And you have a 0 here. When we plug in 2 here, when we plug in 1 squared is 1 times 2 is 2. Then we have 8 again. And finally, when we plug in 3, when you plug 3 in here, 3 squared is 9 times 2 is 18. All right. First differences. Let's kind of just reveal this for a moment. You can kind of see. We have right here, this is going to be negative 8, or rather, yeah, 8 minus 18. That's a positive 8 right here. So this is 8 minus 18 is negative 10. Then 2 minus 8 is negative 6. 0 minus 2 is negative 2. And then 2 minus 0 is 2. 8 minus 2 is 6. And then 18 minus 8 is 10. All right, so now we're on to the second differences. Let's take a look over here. Let's do negative 6 and then minus a negative 10. So negative 6 minus, that's going to be about 4. All right, so let's reveal these. Okay, and you'll notice all of these are going to be 4. And I know I didn't reveal this just yet right up here, but what do you can kind of see this degree is a 2, the exponent is a 2, so this one's going to be quadratic, and that means that the second differences are all, and what's the word I'm about to say? Constant. And for a linear, the first differences are all constant. All right. I'm going to skip ahead, and I'm probably not going to do these. I will reveal these, though. Here's your linear, and for part D, that's going to be your quadratic. Easy enough. Okay. We pretty much answered these questions, and I might just ask these in the video. So, linear functions. What do you notice about the first and second degrees? Well, for linear functions, here we go. For linear functions have constant first differences, and the second differences are 0. For quadratic functions have a changing first difference, and a constant second difference. It says here we're going to sketch these graphs represented by these equations. All right. Now, you haven't had that much experience sketching graphs without a graphing calculator, so I'm a little bit concerned about that. But I'm gonna take the approach as if you understand this whole y equals mx plus b piece. So we have y equals mx plus b. Notice b is equal to 0, and that is always our y-intercept. So 0, 0 is a point that we can begin from. There's 0, 0. And then this 2 is our slope, and that's 2 over 1. So rise 2, run 1. Rise 2, run 1. Rise 2, run 1. We can put these little points on here. And let's go ahead and connect these. Kind of see what this is going to look like. There we go. There is our line. I'm certain that all of you could graph that on the graphic calculator without any kind of issue at all. Next one is a quadratic. Now, you absolutely don't have experience graphing these and just sketching them. We could make an XY chart, if you would like, and start inputting values, for example, -2, -1, 0, 1, and 2, and start plugging them in, and this would look something like this. Plug the -2 in here. This is going to be 2 times -2 squared. Let's do the workout. This is going to be 2 times 4, and that happens to be 8. So -2, 8. Here it is. I'm going to watch the cursor here. -2 and then up 8. It's right here. Let's plug -1 in. We plug -1 in right there. 2 times -1 squared. That's going to be equal to 2 times 1, which happens to be 2. Okay. So that's going to be the point, -1, comma 2. The left one, up 2. Then 0, when we plug 0 in, we get 0. When we plug 1 in, we get 2. When we plug 2 in, we get 8. So it kind of has this mirror image. On the other side, we'll paint these green. And watch this. Let's connect these two. See this quadratic happen. And there it is. There's the sketch. Now keep in mind, you're going to have a graphing calculator with you at this point. So there's the sketch of those two graphs. These two graphs, C and D, sketching these two, page 874. All right. We have M. Our M here is -1 over 1. And our B is equal to, it's actually equal to 4, so I have a y-intercept of 0, 4. So 0, 4 is going to be located right here. We have, here's 1, 2, 3, 4. Right? And now let's do a slope of down 1, right 1. Okay, keep that in mind for a moment. Down 1, right 1. So we're going to go down 1, right 1. And then down 1, right 1. We've got that line. Let's go ahead and attach these. You can just take out a ruler and draw through, but there's your line. Let's put arrows on the ends. Next one, you'll notice we have an exponent of a 2. It's a degree of a 2. And also notice that is a negative. So we know that this is going to open down. All right, it's going to open down. Well, we could do a bunch of calculations here, but just know I want you to focus on knowing it points down, enter it into your calculator for a now, and it's actually just going to look like this. It's going to have a point. Here, let's make this point a little smiley face. Okay. We're going to come up here. That is going to be your actual vertex. And it's going to look like this. And you can test this on your calculator if you want. go ahead and graph these and connect them. And there you go. You might be wondering, well, how in the world is he getting these points right here and here and here? Well, go ahead on your calculator and you'll be able to actually access the table. So on the table it will look like this. Y equals, I'll move this over here so you can see everything. Let's clear these out. Let's just do this simple function of negative x squared and then plus 4. If I go over to second and then graph second table, you can see all of these points. There they are. So I have a point of negative 1, comma 3. Well, that's right here. Negative 1, comma 3. And look at this point. That looks like it's going to be 3, comma negative 5. Let's see if that's up there. 3, comma negative 5. Aha. Right here. 3, comma negative 5. We can do that for all the points. And that concludes this video.